Okay, so hopefully this problem now is solved, and hopefully everybody now, after talking about this, is able to solve this for themselves. So have a go at that. See whether you can do it now with well, it's basically almost written out on the board. So this is basically the thought behind it. So you know this expression. Don't worry about this mathematical expression, but effectively, if you would look back to the Smoluchowski theory, and you know, basically to calculate the collision rate, which was A times the flux, the area times the flux. We had for D1 A times pi times the radius to the power 2 times the diffusion coefficient, the self-diffusion coefficient of your particle, times the gradient. The gradient of the particles as a over r is the distance from the central particle. And the thing what you add now is a potential barrier. So with Smoluchowski, we assumed that every collision was successful, but now you no longer do that. Now you say, okay, there is a certain energy that makes this easier or more difficult. So you can think of a barrier, for example. An electrostatic barrier would be if two things would be charged with the same sign, so two objects are negatively charged, and they come closer, and then they start to repel each other. So the likelihood that collision is successful is more difficult. Imagine, I think the easiest thing to imagine is with two magnets, right? You've got two magnets, and you have the poles, the opposing ones, yeah, close to each other, and it's very, very difficult to push them together with a certain force. Yeah, and you just have to push harder and harder in order to push the two things together. Now, if you would invert the magnets, then it becomes even easier than random motion, and the same thing happens here. So you put a potential in between, and this gradient can either be attractive or repulsive. Now, I know that if you want to keep your particle stable, you want to put a repulsive gradient in there. Now, this was realized already in 1934 by a guy called Fox, and he proposed this, and he basically came up with a Fox constant almost, which is like W in this case, which was the radius over K fast over K slow. So K fast meaning Smoluchowski, every collision is successful, and K slow meaning every collision is successful, but it could be even faster if there would be attraction as a result of this gradient. Or in most cases, you want to have the opposite, obviously, because you want to guarantee that there's colloidal stability. And in that particular case, you put a barrier in place, and then you want to know how high this barrier is. So that's important. Okay, so let's do one example of a system where collision is even easier, because on the long range there is an attraction between two objects. So let's pick a large object that has a positive charge, and then put particles in it that have a negative charge, and then see what happens. So here you see an example. This is an example taken from our group, published last year in JACS. And what you see here is polymer vesicles. So polymer vesicles are quite an interesting species, kind of suprastructure by themselves. So if you look at picture A, this is a picture taken from the work by Discher, who is one of the pioneers or someone who's worked a lot in this field. And you see, well, little picture A, a twin-tail surfactant. That's like a classical, you know, phospholipidic type of vesicle, or DODAP, something, a quaternary ammonium salt with some two large alkyl chains, and you can form a bilayer. And obviously, if this bilayer curves, you can just create a hollow structure with no edges, right? And then you'll end up with a vesicle. Now, if you think about that, a phospholipid, for example, would have a negative charge and some large alkyl chains, or DODAP, which has a positive charge and some large alkyl chains. So you have a polar bit and a non-polar bit, and depending on the packing parameter, we'll come back to that later, these things will form vesicles or not. So you can design larger molecules, polymeric molecules, for example, block copolymers, that would behave in the same manner. So you can make hollow objects that are basically have a bilayer as their characteristic structure. Now the thickness of this bilayer can be tuned relatively easily by block length. So what these things are very interesting for drug delivery capsules, and there, you know, a lot of groups are working on this. So if you do a literature search on the word polymersome, which is like a bit of a trendy word for this, or even like, you know, just the word polymer vesicle, then you'll find at least 10,000 papers over the last 10, 15 years. So, and now the interesting thing comes that, you know, how would an object like this now respond when it bumps into another colloidal object? So what if a vesicle now interacts with a particle? What would happen then? So, and why do you want to know this? Well, for example, you know, drug uptake or nanoparticle toxicity. In that particular case, that object goes through your cell wall. And maybe your cell is a little bit more clever and has an active process, endocytosis, for example, that the biologists claim, but maybe there's some other things that we don't know yet. So a model system would be quite interesting. So what we did basically was just this Smoluchowski trick. So we made a cationically charged polymer vesicle. So we used the MIMA as one of the monomers, which at low pH protonates, so it's a tertiary amine. So you get a vesicle, and the outside is positively charged. And then we just added different particles, excess of different particles. So in picture A here on the left-hand side, it's a cryo-SEM image of a vesicle covered in monodispersed hard spheres of polystyrene. And as one thing is already really interesting. So if you think about the collision process, that's random. And these things on the surface are ordered. So what is the reason? So one of the things could be that once they're on the surface, they can ice skate over the surface, or maybe they just drag a bunch of these molecules alongside with them as a little island or a raft. Biologists like to call this potentially a raft. Imagine that this particle is quite similar to a protein, right? We don't know where it lies on the surface, maybe a little bit in it, and it just could ice skate over it and then have a better interaction and therefore crystallize, because this looks almost like a crystalline structure. But then you would imagine, you know, if the system would jam, as in maybe you can't get this perfect practice, so maybe things are reversible. Yeah. Now in picture B, that's quite similar, but that's a TEM image, and now we use smaller silica particles. And again, you can see it's a bit more difficult to see. It's kind of fully covered. Now, if you understand that a little bit better, then you can just do some fun chemistry, right? So everybody knows that Smarties melt when you heat them up. So polymer spheres can also melt when you heat them up. So if you would pick something that has a lower glass resistant temperature, like for example butyl methacrylate, and you cover that in your sphere, then when they touch each other, they film form, and effectively you have an original vesicle that's now transformed into something more like a vesicle in a plastic bag. Yeah? And picture D would be, what if you have a particle that is, again, it's a polymeric particle in this case, that is made out of 60% acrylic acid, 40% ethyl acrylate. And if I trigger the pH, raise the pH, then suddenly this particle completely disintegrates and becomes a gel, a hydrogel. So now you have a vesicle in a hydrogel. So with these kind of attractions, you can have quite a lot of fun. And these things, they basically have a relatively strong attraction with respect to the underlying originally cationic surface. So you can mix and match. And in order to understand this, you know, physically better, you have to do simulations, which are very high-end. And in order to get that right, to know what, you know, how do you know whether your simulation makes sense or not, you have to know something about, you know, what's called pair potentials. It's like how do two objects interact with each other. Now, on a molecular level, this comes down to, you need to know about van der Waals attractions or repulsions. You need to know about dipoles, induced dipoles, charges, hydrogen bonding, hydrophobic effects. But on a particle level, all those things are also valid. And they're multiplied. Because, you know, a particle is nothing more than just a large clump of atoms all together. So you have a bunch of atoms interacting with a bunch of atoms rather than just one and one. And then the theory, you know, becomes a little bit more complex related to that. So let's make a first step into this. So we want to know a little bit more about this barrier. And the barrier effectively is what we need to know if I have two objects on a certain distance from each other. So let's just talk about just two objects, not multi-body ones, right? So infinite dilution, there's only two objects. And from a certain distance, these things start to feel each other. They either can have an attractive interaction or a repulsive interaction or a combination, maybe. And then you just, in your mind, you just bring them closer and closer and closer, and you just see how this, well, this pair potential, how that develops. And then the main question is, you know, is there a common ground between intermolecular forces and interparticle forces? Is there maybe something that relates to it? A really good book on that is Jacob Israelakvili's book on surface forces. I think that's a third edition. There's a third revised edition out now. So if you like this stuff, that's the absolute #1 textbook to get, I would say. So where does this come from? Well, this started, so we zoom a decade back, a century, or longer than a century. This started with van der Waals. The notice that two atoms in this case, or two molecules, if you look at a gas, had an interaction with each other, right? Because he came up with this van der Waals equation, and not only he took into account excluded volume. Excluded volume, in a way, is like almost like your Pauli exclusion principle, right? You can't have two bits of matter that overlap with each other. Yeah, maybe in physics sometimes now you can have stuff that can, but typically that is a repulsive type of interaction, right? And then the intermolecular forces was to account maybe for attraction or even stronger repulsion between two ping pong balls in this case. So van der Waals was, you know, one of the first. Actually, he did this for his PhD. It's quite interesting. So chapter 7 of his PhD thesis was this, and then he won a Nobel Prize on it. So there you go, guys. A few years from now, then that's what you need to do. So related to that, this guy, Wilhelm Ludwig proposed just proposed an interaction potential with a repulsive and an attractive term. So under the definition is that the potential is negatively charged, has a negative sign if it's attraction, and it's positive if it's repulsion. So it's just a matter of definition. Yeah? And then all he said, it was just like a bit of a power type of expression. So he just said there's a term A divided by the distance between the particles to the power n, plus a term B divided by the distance of the particles to the power m. And that was it. And so it's a very, very generic one. And then you can kind of rearrange this a little bit. So you could take the top one and write it more complex, just in the middle. And then basically what people have done is that in this particular case, that sigma, for example, is the value of r, the distance between the objects, in which this potential reaches the number 0. Because obviously if you have attraction and repulsion, somewhere in most cases you'll hit 0 at some stage. Yeah? And then epsilon, in this particular case, would be the depth. So what's the minimum of this energy curve? And then, you know, it transforms into that. But the top one is exactly the same as the middle one. So now one of the ones that you might know, which is a special case of the Mie potential, which is used for molecular interactions a lot, is the van der Waals equation. Or sorry, the Lennard Jones potential. So John Edward Lennard Jones came up with a Lennard Jones 612 or 12-6 potential. That one is depicted there at the bottom. So you'll have basically a repulsive term that scales to the power 12, or R over the power 12, yeah? And the attractive one is to the power 6. And now you kind of got to figure out, you know, how that works. So you have, in the top equation, R to the power 6, or R to the power 12. R to the power 12 is pretty, you know, on a short distance, because it dampens out really quickly. So you get short length repulsion, and R to the power 6 is slightly longer distance, dampens out slower. It's like a relatively long-term attraction term. And you combine the two, and you get a picture. So this is like just conceptually how you can go from strong to weak. So if you want to make this interaction stronger, so depending on the textbook, by the way, Israel really uses W, and other books use VT. So V is used for potential energy, but also W is used for that. So, and then X is just your A or your B, and if you make that number larger, obviously you get stronger. If you make the number smaller, it becomes weaker. And long range, N, if you make N smaller, it becomes long range, and if you make it larger, it becomes shorter range. So what does it look like? So take the Lennard Jones potential, and you just plot it, and that's the graph you get. You get a solid line. So in this particular case, that if your two objects, or your two molecules, or your two atoms in this case, are infinitely far from each other, obviously there's no interaction, and then become closer and closer and closer, and you basically move, you get an attraction. You get a van der Waals attraction in this case. Yeah? And then when you come too close, you get a repulsion, because you have, you know, two overlapping states of matter. So the total graph will look something like the black line. Yeah? And now you might wonder, why do I care about this black line? Well, for particles, this applies as well, but more importantly, in analogy to this, if you take the first derivative of energy, you get force. So the first derivative of this pair potential graph is the dotted line, and that's the force curve. And forces can be measured directly with STM or with AFM. So now we could actually do an experiment and verify whether these things experimentally are right or wrong. And then from the other point of view, all the way from quantum levels up, you can simulate and see whether you get these curves right or wrong. And that basically means that you know how strongly atoms, in this case, or molecules interact with each other, but also if you do this, an experiment between particles, how particles interact with each other, and then you know exactly what those force barriers or, what they are. And you can explain a lot of interesting things with this. So one of the math exercises I want you just to have a look at, but we haven't got time now to do this, is that once you've got this graph, you can calculate a lot of things. So let's just go back to this graph, right? Once you have this graph, which is nothing more than that over there, then you can calculate what R0 is. Basically, where does my energy curve hit 0? Yeah? I can calculate where the minimum lies, and where the minimum lies is the same as where the force curves hit 0, and then I can calculate where the maximum force that you can feel is, which is RS, is where the first derivative hits 0, so effectively the second derivative of the energy curve. So you can just figure that out completely, and if you put the numbers in, then you know whether you can measure something and how large these forces are. So that's what that exercise is about. So I'll have a look at that, and then we'll come back to this in more detail. But so here are the answers. So I'll upload those as well. So see whether you can do this for yourself. And then here, I just want to show you why this is important. So here you see a relatively recent paper in which they basically see how low can I go with an A of M. What's the smallest thing that I could measure? So they had literally a CO molecule absorbed on a clean metal surface, and then they had an A of M tip which was made out of the same metal, or they had an A of M tip with one molecule of CO absorbed onto the tip. And then they did both STM and A of M. And with A of M, you kind of measure a frequency of the cantilever, and the frequency at which the cantilever kind of responds is linearly correlated to the force curve. So that force curve is the one I just told you about. It's the first derivative of the pair potential. Yeah? So if you could do your A of M experiment properly, you're able to basically see, you know, how does, in scenario A, a metal tip with, in the ideal case, one atom interact with the CO, and how does a tip with one CO molecule interact with one CO molecule? Now the difficulty is that the tip by itself also interacts with the underlying surface. So it doesn't only interact with the CO molecule. The CO molecule is not very big, so there's also an interaction of the underlying metal surface with all the atoms in the underlying surface and all the atoms in the tip. So and that interaction kind of dampens out the larger you make the system. So it's not a very easy question to solve. So what they did is they did these measurements really carefully, and they also modeled the things a little bit with DFT calculations. So that's the kind of stuff that here in the department, you know, Mark, Roger, and Rob Deeth get up to in their free time. So they pick a cluster of 4 metal atoms and then just look how it interacts with one CO molecule. Just to see, you know, if you move it closer, do you get an attraction or a repulsion? So now, if you look at the metal tip by itself, red means there's an attractive interaction. So a naked metal tip feels a CO molecule, there's an attractive interaction only. However, if you have a CO tip, you get an attraction, and then later on you get repulsion. So CO and CO repel each other, whereas CO and metal, the end result is that you just get a covalent bond between the two. Yeah, so there's no repulsion in that particular case. Well, if you get closer and start pushing crazily, then probably you will. But and what they found is that the A of M data was pretty spot on with respect to the DFT data. So this is what you get. So you get your experimental force curve and your simulated data, and they're pretty close. Now the difficulty is to get it completely right, because not only, so you see here in picture B that there's lots of interactions possible, right? So in the top one is the easiest one. So you have an interaction between the surface, the metal surface and the tip, between the metal surface and the CO molecule, and between the CO molecule and the tip. But if you have a CO molecule on the tip, then you have way more interactions. And then the bottom scenario gets even more complex, because these CO molecules, they can wiggle, they can move, yeah, so they can bend. And then obviously the distance is not easily defined in the Z direction anymore, because you'll bend into the XY plane. So that's what these 3 pictures here at the bottom say. So depending on where you are there, you get a different interaction as well. And obviously we've seen in the previous picture that these 2 things repel each other. So when they come close, they will bend away from each other. So you'll get, and that's what's depicted over there. Yeah? So hopefully, to sum up, for now, you see that pair potentials, the interaction between 2 things, is really important. We will get back to that only with particles, but in order to do that, we'll spend also 1 lecture on dipole interactions and things like that, in order to put it into molecular context as well. And we'll do that Not tomorrow and Wednesday, we'll do that in 2 weeks' time. Tomorrow and Wednesday we'll do some light stuff, so no physics, and we'll look at self-assembly and at interfaces and self-assembly in solution. All right, thanks for coming.